Okay. Let's start with a mental image. You're walking down a busy city street, or maybe you're standing in line at a bank. You look up, and what do you see right there in the corner of the ceiling?
Usually a little glass dome, a security camera.
Exactly, a little glass dome. And for decades, I mean, we've looked at those things and just thought, that is a passive object. It's an eye.
Right. It just sees things and sends the video down a long cable to a dusty closet somewhere.
Right, it's essentially a dumb pipe for pixels.
Historically, yeah, that's exactly what they were. Just sensors capturing light and moving it somewhere else to be processed.
But what if your security camera could run AI models directly on the edge?
Then I'd say we're ready to dive into today's topic.
Welcome back to the deep dive. Today, we are looking at something that fundamentally changes how we think about edge AI. We are cracking open a specific GitHub repository from Axis Communications called acap-native-sdk-examples.
It is a bit of a mouthful for a title, I know.
It is, but honestly, don't let the name fool you. This open source repo from Axis shows how to build native ACAP apps in C++. The promise is basically turn an IP camera into an AI edge device in minutes.
And it is worth noting, this isn't just some theoretical exercise. This repository has real traction.
Yeah, I saw the stats on this one.
Right, we're talking 78 stars and 42 forks on GitHub. In the world of embedded camera development, that is a bustling community.
It's the cool kids table of security camera dev.
Yeah, you could say that. It serves as the blueprint for the Axis Camera Application Platform, or ACAC, specifically the native SDK.
So before we get into the code, because we are absolutely going to get into the weeds of C++ and Docker here, we really need to establish the why.
The why do we need to bring rain inside a camera?
Exactly. We have the cloud. The cloud is infinite. Why not just stream everything there?
Well, it really comes down to physics and economics. Think about the old way. You have 1,000 cameras in a large facility, say an airport.
Okay, so that's 1,000 separate video streams.
Right. And if you are streaming high-definition 4K video from all 1,000 cameras to a central server 24/7, you are generating an absolute tidal wave of data.
You're basically melting the fiber optic cables.
Essentially, yes.
Yeah.
The bandwidth costs are astronomical, and then you have latency.
Right, because the video has to actually travel.
Exactly. If you are trying to spot a safety hazard, like a forklift driving way too fast, you can't wait for that video to travel to a server farm 3 states away, get processed, and send an alert back.
By the time the alert comes back, the accident has already happened.
Exactly. You need that decision to be made in milliseconds. You need the compute to be right there where the data is born.
Which is the literal definition of Edge AI, process real-time video streams directly inside the camera hardware.
Exactly. And ACAP is the platform that lets us do this. But the sources highlight that we're looking at the native SDK today.
Yeah, who is this for exactly? Because I know Axis has easier, high-level ways to write apps.
This is for the power users. This is for the developers who want plug-in style applications with native ACK SDK integration.
So you aren't writing a script that just floats on top of the OS?
No, you are writing code that sits right next to the metal. It integrates closely with the AKXOS OS Linux environment and the underlying chip architecture.
You're basically shaking hands with the hardware at that point.
You are. It is all about squeezing every single ounce of performance out of the device.
Which explains the language breakdown we saw in the repo. I was looking at the stats, and it is honestly pretty aggressive.
It is a monolith of C and C++.
Yeah, 81.9% C. Then a solid chunk of C++5. There is a dusting of Python and shell script, but this is fundamentally a C environment.
Right.
In a world where everyone is obsessed with Python and JavaScript, why are we going back to C?
Because on the edge, efficiency is the only thing that matters. When you are running on a camera, you have constraints.
Like power constraints, right?
Yeah, a limited power budget. You can't have the camera overheating and shutting down. You have limited RAM.
You don't have the luxury of a garbage collector cleaning up your messy code every few seconds.
Exactly. C and C++ give you manual control over memory. You decide when every byte is allocated and when it's freed.
It's like driving a stick shift versus an automatic.
That is a great analogy. It is harder to learn, but if you know what you're doing, you have total control over the engine.
But here is the problem, and I speak from painful personal experience here. Developing C++ for embedded hardware is usually an absolute nightmare.
Oh, you mean the cross-compilation trap?
Yes, the classic, it works on my machine problem. I'm sitting here on my Windows gaming rig or my MacBook. I have an x86 processor.
But the camera is running on an ARM chip or a specialized ARTPEC chip.
Right, so if I compile the code on my laptop, the camera looks at it and says, I have no idea what this is.
That is the language barrier. And historically, fixing that meant setting up a really complex toolchain,
You'd spend days finding the right compiler versions and linking libraries.
dealing with weird, obscure errors. It is a massive barrier to entry.
It's enough to make you quit before you even start. But this is where the acap-native-sdk-examples repo does something really smart.
The Docker workflow. A Docker-based workflow makes cross-compilation simple.
For the listener who knows Docker as just that thing DevOps uses, walk us through how it helps me program a camera.
Think of it this way. Axis has created a Docker Hub image. This is a pre-packaged virtual environment.
Like a suitcase.
Exactly, like a suitcase that contains everything you need. The specific compilers, the SDK headers, the libraries, the build tools.
So I don't have to install a weird compiler on my actual laptop.
Not at all. You just pull the Docker image, you write your C code in your favorite text editor on your machine.
And then what?
Then you tell Docker, hey, take this code and build it inside that container.
So the container acts as a translator.
Yes, it takes your code, compiles it using the tools inside the image, and spits out an executable file that is perfectly fluent in camera.
That is incredibly slick. It bridges the architecture gap without me having to become an expert in compiler flags.
Exactly. It completely decouples your development environment from the hardware requirements.
Which means you really can be up and running in minutes, not days.
That's the beauty of it. So we have our environment set up, we've got our container, we are ready to write some C++ playing.
The repo is organized by topic, right? Like audio, machine learning, streaming. Let's start with the basics, seeing.
Right. If you're building a camera app, step one is getting the video. The repo has a specific example called VideoStream.
Now, is this just like opening a video file, like a basic open video.mp4 command?
It's much more powerful than that. VideoStream shows you how to interface with the video service, the video display output service on the camera.
Leveraging things like GStreamer underneath, perhaps.
Exactly. GStreamer is a big part of this ecosystem for handling media pipelines. It's not just giving you a picture, it's giving you access to the raw buffer.
The raw, uncompressed pixel data.
Yes. And crucially, the metadata. Every frame comes with data about its timestamp, exposure settings, and format.
Which you absolutely need if you want to run an algorithm on that image. You don't want a JPEG that's already been compressed and lost a ton of detail.
Precisely. So once you've tapped into the optic nerve of the camera, you want to add the brain, the machine learning section.
This is the stuff everyone wants to do. This is the edge inference on Axis cameras we've been building up to.
This is definitely the headline feature. The repo provides several examples, but the heavy hitter is Object Detection YOLO 5.
Ah, YOLO, you only look once.
A classic real-time object detection architecture. The example code demonstrates how to take a YOLO model and run it locally on the device.
To identify things like people, cars, backpacks, bicycles, right.
Right, and there was another one that caught my eye, actually. Object Detection-CV25.
Yeah, I saw that. What is CV25?
This is where we get into the hardware specifics. CV25 refers to a specific Ambarella system on chip that powers some of these devices.
Hardware optimized deployment.
Exactly. This example is fascinating because it doesn't just detect the object, it crops the image of the object and saves it as a separate JPEG file.
So it's acting like a curator. It's saying, I don't need the whole street. I just need this high-res photo of the person walking by.
Which hugely optimizes storage and focus. But the real technical gold in this repo isn't just the C code.
What is it then?
It's the guides on how to get the AI model ready for the camera. Did you see the folders labeled TensorFlow to Lerod?
I did, and I have to ask about that name. Lerod. It sounds like an ancient deity or a sci-fi villain. All hail Lerod. What is it, actually?
It's a lot more helpful than a villain, I promise. Lerod stands for something like Live API for running object detection.
Okay.
It's a helper library and daemon that Axis built.
Yeah.
It is the bridge between your generic AI model and the specific silicon in the camera.
Unpack that for me. Why do I need a bridge? Why can't I just run TensorFlow directly on the camera?
Because a generic TensorFlow model is heavy. It is designed to run on a massive server with unlimited power.
And a camera is not a massive server.
Right. The camera has a specialized accelerator, maybe a DLPU, a deep learning processing unit, or a TPU.
Oh, so Lerod helps map the math of your neural network onto that specific chip.
Precisely. It translates the abstract math into hardware instructions.
So the guides in the repo, those TensorFlow to Lerod folders, they walk you through that translation process.
Yes, they walk you through taking a model, quantizing it, which means simplifying the math slightly to make it faster, and converting it into a format Lerod can use.
And the repo lists guides for different chips, right?
Mm.
I saw ARTPEC 7, ARTPEC 8, ARTPEC 9.
Yes, and that is critical. An RPEC 8 chip has totally different capabilities than a CV25 chip. The repo gives you the specific recipe for each one.
It's not a one-size-fits-all situation. It is highly optimized.
Exactly. So once you've optimized the model, you use the Vito Larid-C example to actually run it on the video stream.
That is the whole pipeline. Capture video with VideoStream, process it with the Larid library using your optimized model, and get the result.
Right. But the camera isn't just a black box that thinks to itself. It needs to tell us what it sees.
Visual feedback.
Yes, the user needs to know what the AI is thinking. There are two main ways to do this in the repo. First, there is AX-overlay.
That's the simple one, right? Just drawing a box.
It allows you to draw playing boxes and text as an overlay layer on top of the stream. It's great for debugging or simple operator alerts.
Like person detected in big red letters.
Exactly. But then there is bounding box.
How is that different?
This one is more robust. It demonstrates a portable way to draw burnt-in bounding boxes directly onto the video source itself.
Wait, burnt-in implies it becomes part of the actual pixel data?
Correct. If you export that video file to hand over to the police or an insurance company, the box is permanently part of the footage.
That is a really important distinction for legal evidence.
Definitely. Now, speaking of processing power, there was one example that really surprised me. Video OpenCL filtering.
Ah, yes, the OpenCL example. Now, OpenCL usually implies GPUs. Are you telling me these security cameras have graphics cards?
They do. Well, they have integrated GPUs, and this SDK unlocks them.
I guess I just never thought about a security camera needing a GPU. I thought that was for gaming or rendering video.
Well, it's not running the latest AAA game, but image processing is all about math.
Right, it's matrix math.
Exactly. Yeah. The VEED OpenCL filtering example captures frames and performs a Sobel filter. That's an edge detection algorithm that makes the image look like a pencil sketch.
And it does this entirely on the GPU.
Explicitly. And that is the aha moment. By offloading that heavy visual math to the GPU, you leave the CPU completely free to do other things.
Like handling network traffic or running the core logic of your application.
Exactly. It's proper heterogeneous computing on a tiny edge device.
That is wildly sophisticated for a device hanging on a pole in a parking lot.
It gets even weirder. The camera can also act as a web server.
Really?
Yeah, there's an example called web server using FastRG.
So theoretically, I could host my personal blog on the security camera outside my house.
Theoretically, yes, you absolutely could.
I am tempted to try that just for the novelty.
Practically, though, you would use it to serve a configuration page.
Oh, that makes sense.
Imagine you build an app that counts cars. You want the user to be able to log into the camera's IP address and see a nice web page where they can adjust the settings.
Or view a live graph of the traffic data, so it keeps everything completely self-contained.
Exactly. You don't need a separate cloud dashboard just to manage the camera settings.
And looking at the curl OpenCL example, it works the other way too.
Yes, the camera can securely reach out to the internet to fetch files or send data to an external API.
Okay, so let's zoom out a bit. We've got a device that can see, it can think with AI, it can use a GPU for image processing, and it can host a website.
It's a Swiss Army knife.
It really is. So what does this mean for the real world? Let's brainstorm some actual use cases.
The most immediate one is what we call smart surveillance. It is perfect for smart surveillance, automation, and edge analytics.
It's about filtering out the noise. The whole boy who cried wolf problem.
Exactly. If your motion detector goes off every single time a tree blows in the wind, you just stop looking at it.
Right, human nature, you ignore it.
But with object detection running on the edge, you can tell the system, only alert me if you see a human or a vehicle.
So you save time for the security guards, but you also save massive amounts of storage. You aren't recording petabytes of empty driveways.
Precisely. But let's go further. Think about automation. We saw AX-event in the repo.
What does that do exactly?
That allows the camera to send and subscribe to events within the Axis system.
Give me a concrete example of that in action.
Okay, imagine a highly secure facility. You have a camera with facial recognition code running via ACAP. A person walks up to the door.
The camera sees them and runs the edge inference.
Yes, the camera recognizes them as an authorized employee. It then uses AX-event to trigger a message to the door controller via AX serial port.
To physically unlock the deadbolt.
Exactly.
The camera is literally the bouncer.
It is. And the critical part is it happened entirely locally. If the internet connection to the building goes down, the door still unlocks.
Because it's not relying on the cloud to verify the face. That is the power of edge computing right there. Total reliability.
That is a huge point. What about audio? We glossed over earlier, but there's an audio capture group in the repo.
Oh, right. So it's not just a visual sensor.
No, and it's very significant. A camera can be a listener. You could train a lightweight model to listen for specific sounds.
Like breaking glass or a car alarm.
Or a gunshot. Or even aggression, loud shouting voices in a hospital waiting room.
Wow, so the camera could trigger an alarm before a physical fight even starts just based on the audio signature?
Exactly. It becomes a multimodal sensor. It's not just looking, it is sensing the entire environment in a holistic way.
It really feels like we are completely blurring the line here. We used to have dumb edge devices and smart centralized servers.
Now the intelligence is completely bleeding out to the edges.
So, to recap, for anyone listening who is technically inclined and itching to try this stuff, explore the repo and start building Edge AI today.
It really is your starter kit. It solves the toolchain headache with Docker. It gives you the optimized paths for the hardware with Layrod.
It basically holds your hand through the hardest parts of embedded development.
It is, without a doubt, the best way to start building for ACAP.
And honestly, it challenges my entire perception of what these devices actually are. I asked this at the very beginning, but I will ask it again now that we know what is under the hood.
Go for it.
If a security camera runs Linux, hosts a web server, executes GPU-accelerated code, and runs complex neural networks, at what point does it stop being a camera?
It's a deeply valid question. I think we are rapidly approaching the point where it's just a server that happens to have a lens attached to it.
A server with a lens, I love that image. It definitely makes you look at those little glass domes in the ceiling with a bit more respect.
It's an incredibly powerful piece of technology just hidden in plain sight.
Well, if you're a developer or just someone who likes tinkering with hardware, I'd highly encourage you to go check out the repo. Who knows what you might make that camera do?
The possibilities really are pretty much endless.
That is all for this deep dive. Thanks for listening, and we'll catch you in the next one.